All right, last half of the new material. So there's a question here. So you want to repeat your question?
Sure. I was just...
Guys, shh.
In the theorem that we were trying to prove, I was a little confused between the difference of big O f of n space and little o of f of n space, and which one's a bit larger than the other.
Mm-hmm.
Can you elaborate on that?
Yeah. So we talked about big O f of n and little o f of n. So here, just informally, big O f of n just means any function that runs that's at most a constant times f of n. That's all it means. Little o f of n means same thing, but it runs strictly asymptotically slower than f of n, asymptotically less than f of n. So example we have on the board, but I'll repeat it here anyway. So 5n squared is big O n squared because it's at most a constant times n squared. But it is not little o n squared because it runs at the same asymptotic rate as n squared does. So therefore, it's not little o n squared. But if we considered instead 5n to the 1.9999, a bunch of nines, as many nines as you want, is little o n squared because it runs strictly asymptotically slower than n squared. So actually another one you can do, if you consider 5n squared divided by log n, so even less of a change than the 1.91, that is also little o n squared because it runs asymptotically slower than n squared. Yeah.
Are those two combined the same theta n squared? Big theta n squared?
No, that's not the same thing. Theta n squared is big O n squared and big omega n squared. So things that grow at least as much of a constant as n squared. So it's either, so here it just means at most a constant times n squared, at least a constant times n squared. So if it's both of them, then it is a constant times n squared. But here it's different. It's saying it runs strictly asymptotically slower.
I mean, both of those combine, the big O and the little o.
Combined to make what?
Like the first sentence you had, or the first
Well,
thing you had there, both of them are true.
Okay, yeah. Yeah, so little o of anything is a subset of big O of the thing. So little o f of n is always a subset of big O f of n. Because the larger one contains all the functions that run asymptotically slower. Because it's at most a constant times a thing. So therefore it's a subset. The little o is a subset of the big one. Think big O contains more things. That's the way to think of it. Okay, any other questions? Yeah, go ahead.
Going back to where I was asking my question, it seems like big O contains things that are smaller than little o.
Mm-hmm.
So then when I think of
Well,
big
what's-
O f of n space being larger than little o f of n space, I kind of get confused.
Well, what do you mean smaller than little o?
Like,
Because there's no such function. The little o contains all the functions that run slower than n, in this case, n squared.
okay.
So if you go all the way down to constants, then that includes all functions that we consider here. So therefore, but big O n squared, in this case, contains all of those and the ones that run in some constant times n squared time. Yeah, you had a question?
Can you just go over this thing briefly with what we were trying to do again?
Yeah, sure. In this, right?
Yeah.
Okay. Unless there are other questions about the little o, big O, whatever. Okay. So the entire idea here is we're going to have this machine have D right here. What D is going to do is it's going to only possibly accept if we get a machine as input. So if we get a machine as input and maybe other things, then what we're going to do is we're going to simulate that machine on this input W, whatever D gets. And then what we're going to do is say, well, we're going to mark off this f of n thing. I don't know whether or not M runs in f of n space. I have no clue. But we're going to say that if it ever tries to access more, then we know for sure M must run in at least f of n space, because it tried to access something past the f of nth cell. Okay? And so we reject immediately. But if it didn't reject at any point, then it uses at most f of n space. But we may encounter a problem in the sense that the machine could still run forever, even if it's not using too much space, more than f of n space. So that's why we put this restriction on here, saying you can't run for too long. It's the same idea as for LBAs, where we checked whether or not they could run forever. Here we just say, well, if it tries to run for too long, then just kill the machine anyway. Okay? And then outputting, so the real, so all those were just technical things. The real meat of this is that last line, where it says output the opposite of what it does. Why do we want to do that? Because this machine, the machine M, not D, the machine M, at that point says, you used at most f of n space, right? D disagrees with it, always, right? Because it outputs the opposite. So therefore, any machine at all that runs in at most f of n space, D will disagree with it, right? Because whatever it did, D will say the opposite. So it disagrees with every machine that runs in at most f of n space. Okay, does that make sense? Cool. So let's see. And then why does this run in strictly more space? Then let's see. Well, let's try to prove this by contradiction. So suppose, let's see. Some machine, so some other machine, let's say M prime, decides whatever the language we just talked about, the machine of this machine D, whatever that is, let's suppose that it actually uses less than f of n space, right? We used some constant times f of n space here because we marked off f of n space, and then maybe we need some more to handle the checking and whatnot, so let's just say a constant times f of n space. Let's suppose that some machine M prime actually does use less than f of n space. So decides that language, L, the thing that we want to show is the statement is not true here. But let's just suppose that it actually is true, that it decides L in little o f of n space. Let's say g of n space. Well, it uses some amount of space, so let's just say g of n, whatever that is. Well, remember, what does little o mean? Then little o says that there exists a constant, let's see, there exists a constant n0, so remember 310 days, where, let's see. Well, we got to say something about this. Well, remember, D can take this input W that can encode any machine. Well, it could encode M prime in this case. So D may run M prime on some input. And then, well, M prime uses, by assumption, G of n space, but D, as we said earlier, may need some constant times whatever that machine takes. So let's say some constant, say D, times G of n space. I know M prime uses G of n space, but D may need some overhead for some calculations and whatnot. So we're just going to say some constant times g of n space. Well, let's see. Well, g of n is little o f of n by assumption. Okay, so there's some constant where this the amount of space that d needed to run this is strictly less than f of n. So where for all n0 at least, sorry, for all n at least n0, then the amount of space that d needed to run m is strictly less than f of n. But consider this input. Consider the input m prime followed by 1, 0 with a number of zeros being n0. So whatever this constant is, to guarantee that the amount of space used is strictly less, we're just going to consider that input, pad enough zeros on the end to guarantee that this will work. Well, the length of this input is strictly larger than n0 because of this 1 right here. So that's why the 1 is there, to guarantee that this input right here is strictly larger than n0. So this tells us input length at strictly larger than n0. Okay, well, because of that, step 4, simulating m prime on w, will finish. But by the construction of d, d does the opposite. And so therefore, this language L, whatever it is not decidable in little o f of n space, because it did the opposite of what the machine said it did. And so therefore, we can claim that L is a language that does run in big O f of n space, but because by this contradiction that we were able to find, is not decidable in little o f of n space. So in fact, we can show that if you use any asymptotically more space than what you had previously, you can decide more languages, at least one, which is kind of cool. So what this shows us is that space of n is not equal to space of n squared, the example from earlier. And this actually shows us something pretty useful. It actually shows us that the languages that LBAs recognize are not the same as decidable languages. Why? Well, what class do all the languages of LBAs belong to? Space of n. But this tells us if you go to even n squared space, not even decidable, forget that, just go to n squared space, you find the language that an LBA cannot recognize, which is kind of cool. So this is tells us that LBAs cannot decide all decidable languages. So that actually is a restriction for LBAs. It's not like you can convert any Turing machine to an LBA. There are some problems that you really do need a Turing machine to use instead of just an LBA. We kind of already saw that that was true because a LBA was decidable, but ATM was not. But here, this gives us an alternate proof of why that's true, which is kind of interesting. Any questions on that? So I'm not going to do it because it's awful, but there's a corresponding time hierarchy theorem. I won't test you on it, which says almost the same thing, which is that exists a language L such that decided in O of, let's say, T of n time, but not, so big O in that case, but not in little o. But here it's not just little o of T of n, it's T of n over log n time. And I'm not going to prove this, and so that you don't have to worry about it. It's just for your own thought. But we'll discuss a consequence of this. But why is this true? Well, the amount of, if we want to actually do the same strategy where we mark off how many transitions we can actually do, but actually computing that, that number, the amount of transitions we're allowed to take, that takes time. So that's why we can't get little o T of n time. And it's actually this is actually another open question. Can we improve to little o T of n time? And no one knows the answer to that. It seems quite difficult because you need to, if you want to use this strategy to compute the amount of transitions you're allowed to use, and that, of course, takes time. It's just, you can't do that in a constant amount of time, so you can't improve it to that using that method. Maybe there's some other way, but we don't know. Cool. Any questions on that? Cool. So I want to talk about one class of languages, and then we'll see why I'm trying to ask about this. So let's define exp time to be a set of all languages that are decided in 2 to the n to the k time for all k. So here it just means an exponential amount of time. So for example, 3-sat can be done here because we can just try all assignments, and then there are only 2 to the n of them. And then, of course, for that reason, it belongs to exp time. What about the relation between p space and exp time? What's that? It actually is a subset. So why is it a subset here? Well, if I can solve TQBF as an example in exponential time, wouldn't that be enough? Or any problem that runs in a polynomial amount of space. Well, I'm just going to sketch it. If you have polynomial amount of space, how many possible configurations do you have? Well, 2 to the number of cells that you use, which is polynomially many. Well, look at the amount of time you use. It's the exponential, essentially, of a polynomial. And so p space is a subset of x time because we can just look at all possible configurations. There are only exponentially many of them. And then, therefore, p space is a subset of x time. So if you're like an AI, for example, and there are a lot of p-space complete problems there, you can solve them in exponential time. But open question, as you might expect, is this a strict inequality or not? Strict containment or not? But I want to ask something interesting here. What about p and x time? Well, it's very clear that p is a subset of x time because p is a subset of np, np is a subset of p space, and this tells us p space is a subset of x time. So it is a subset. But can you say anything stronger? What does the time hierarchy theorem tell you? Well, it tells you if you have any amount of time that you use, then essentially if you have a smaller amount of time that you can use, you have fewer languages you can recognize. Well, if you have exponential time versus polynomial time, isn't every exponential larger than a polynomial at some point? So what can I say here? It's a strict containment. So this is a strict containment. So there, and you can actually find such a language. So if you've defined, for example, X time completeness, that problem cannot be in P because it's the hardest problem in X time. So if you want an example of one, if you think of generalized checkers, so if you have like an n by n board and you want to ask, can this player win from this particular configuration? That's X time complete. So so as you might expect the headlines to say, there's no efficient algorithm to solve checkers. Actually, no, it's chess, sorry, not checkers. Yeah, so there's a whole like game theory between P space and X time complete stuff. But let's assemble the four classes we've been talking about. So we saw P was a subset of NP, non-deterministic polynomial time. Then P space, which we saw was equal to NP space, which we just argued was a subset of X time. We don't know if for each one of these containments whether or not they're strict or not. So I don't know if P is different from NP. I don't know whether NP is different from P space, and we don't know whether P space is different from X time. But what do you know now? They can't all be equal here. So at least one of them must be a strict containment, but we don't know which. So, which is pretty shocking if you think about it. At least one is strict, but no idea which. And the vast majority of people think that all three are strict because if you think about it, P is different from NP, or it seems like it's different from NP because all of these problems that are NP complete, we can't seem to find a poly algorithm for it. P space seems harder than NP because you're given unlimited time and potentially many configurations that you could visit. And X time seems is harder than P space because it's just such a long amount of time compared to the amount of space you use. But it's just impossible with current techniques to prove any one of them to be strict, but at least one of them must be. Yeah.
So the definition of X time, was it a set of languages we can decide? Let's say.
Yeah, that you can take for some value k 2 to the n to the k time.
To decide.
To decide that language, yeah.
So the language has to be decidable in any of these.
Yeah, it has to be decidable, yeah. Mm-hmm.
So anything that's undecidable isn't it?
It's way beyond X time, yeah. Other questions? Okay, so let's talk a little bit more about some of the more exotic stuff. So maybe some of the more recent research stuff that, and by recent I mean 50 years ago, but recent relatively. So of course we don't know whether P is equal to NP, and we don't know whether NP is equal to P space. So what most people do is they just go off of the assumption that P is equal to NP, or P is not equal to NP, then this occurs. Okay, so it's not like we're just in an infinite chasm of wonder or something about whether they're equal or not. We're just, for this problem, if they are different, then this is true. Or if they're the same, then this is true. And most people think that they are different. But of course, as we all know, things may not be what they seem on the surface. So what some people a long time ago thought, well, what if P actually does equal NP, right? So that might be a question that you may want to ponder. So what if P actually does equal NP? And then if this is true, what else is in NP? And this goes back to that the low for itself problem that I asked you to do in your problem set. So I asked you to show that p to the power p is equal to p. So this is actually why I asked that question, going back to that. So, well, consider this. So if p is equal to np, then if we consider p to the np, so that means I have polynomially many queries to, let's say, 3-set or something like that, oracle, meaning I have a zero-cost question that I can get an answer for about 3-set. So maybe I can present a formula and it'll tell me instantly whether it's satisfiable or something like that. Well, if it does equal that, then this is equal to p to the p, which was equal to p by the problem set. And then the first equality is because of that assumption, p equals np. Well, it seems like we can actually build this hierarchy as high as we want. But if p is not equal to np, then if we have this additional power of putting np into the exponent, maybe we can get additional power out of that. So what this is called is the polynomial hierarchy. And so I'm going to draw a little figure. So here at the, I guess I'll do it at the top. So here at the very top, we're going to have p, just ordinary p. And then we're going to have 2 branches. So here, so the arrow here means is a subset of. So p is a subset of the next 2 layers, which is np, and the other side is co-np, the complement of the languages in NP. So p is a subset of NP, because we've seen that. Why is p a subset of co-NP? Well, is p closed in the complement? We don't know whether NP is, but do we know if p is? Why? We'll just flip the answer. It must run in a polynomial amount of time, whether the answer is yes or the answer is no. So just flip the yes and no answers. So it still must run in a polynomial amount of time. So therefore, p is closed in a complement. We don't know whether np is or not. So that's why I wrote 2 outgoing arrows. If p and np are the same, then np equals co-np. But we don't know whether that's true. But we're going to go one level deeper and say, what if we had NP, but we have polynomially many non-deterministic queries to a, let's say, 3-set. So we can define something that looks like NP to the NP. So like, yeah, like a machine that runs non-deterministic polytime, and it can at any point ask a oracle, hey, is this formula satisfiable or something like that? And then we can do the exact same thing on the other side by going co-NP to the co-NP. And then it's not too hard to prove, but I won't prove it. The arrows also go across like this. And then we can go down one level deeper, say NP to the NP to the NP. And then arrows go across. And then we can just keep going in this fashion, as high as we want. Okay? So this thing is the polynomial hierarchy. So we can start at polytime, then we can upgrade to NP if we want, then we can go with an oracle to NP, then with an oracle to an oracle with NP. So we can keep going as high as we want. Well, so what are we going to call this? So PH, which stands for polynomial hierarchy, is the union of, well, we gotta define each of these layers. So the beginning layer, I'm gonna call sigma 0. How did I do it? I'll do the actual notation. So I don't know why it's like this, but it's sigma 0 to the power p. The p up here doesn't actually mean anything. It's just for notation purposes. Then the next layer is sigma 1 to the p. Next one is sigma 2 to the p. And then sigma 3 to p, 4p, whatever. So then the Pauli hierarchy then is just the union of sigma I to the p. I'll just change this to I. So it's just the union over all these layers on the right side. You could define it exactly the same going down the left side, but I'm just going to stick to the right side for clarity purposes. Okay, I'm not going to prove this, but one of the reasons we introduced TQBF is if we restrict the number of quantifiers to I quantifiers, so TQBF allows for any number of quantifiers, but if I restrict you to I quantifiers, or say exactly I, then that belongs to sigma I to the p. So if we consider something of the form exists x1 for all x2 or something like this, exists x3, etc., then whatever quantifier I, xi, then a formula, then this belongs to, the problem can be decided in sigma I to the p. And the basic proof of that is you can just ask the oracle for the first I minus 1 layers and then run the actual algorithm on the last layer. And so therefore it's in sigma I to the p. Because if you have sigma I to the p, you have I minus 1 oracles, and then you just run each of them on that. Okay, cool. So what does that tell us? Well, since this is a special case of the TQBF formula, TQBF problem, which is p-space complete, then this tells us that for each one of these layers, every single one is a member of p-space as well. So in fact, pH is a subset of p-space. Okay, so, and in fact, since pH contains NP because it's one of the layers, then it's between NP and p-space. So it's a way of both of looking at what happens if you have P and NP being the same, but it's also a way of looking at, well, how could we try to separate NP and P space? And of course there are many other techniques, but this is one of them. But we're going to actually show something really, really shocking. And it's actually very, yeah, go ahead. Great question. We're going to actually show something that makes it seem like there isn't one. Sorry, that they're not the same. But other questions before we show that. We showed that TQBF is p-space complete. You may wonder, well, does pH have a complete problem? Or does sigma I to the p for some value of I, does that have a complete problem too? And it's actually unlikely, we don't know whether that's true, but it seems unlikely that that's true. So what is the quick theorem we'll prove? And it's actually very, very simple to prove. So if a Pauli hierarchy complete language exists, then pH has only a finite number of levels. So it may seem like, just by intuitively looking at this diagram, that each layer is strictly going to get you more languages every time. But if this theorem says, if there's a complete problem for the entire hierarchy, then there's only a finite number of layers, meaning that if you look at that last layer and then try to put another oracle onto it, so like you try to increase the power of it, you actually don't increase the power of the, you don't get any more languages by doing so, which is pretty interesting. Most people think that this hierarchy is infinite because it seems like you really are getting more power every time, but so that it seems unlikely that there's a complete language. But how would you even prove this? Well, it's very simple. What does complete mean in a general sense? What does complete mean?
Every problem in pH reduces to
It reduces to it, but what's the other thing? It belongs in pH, right? If it's complete for the pH class, it belongs to the pH class. So let L be a pH complete language. We don't know if it exists, but let's just assume it exists. Then it must live somewhere in that hierarchy. I don't know where it lives, but it lives somewhere in that hierarchy, right? Well, let's say L is in sigma j to the p, the jth layer, whatever that is, some finite layer it must belong to. Well, what was just mentioned about being complete, everything in pH reduces to this thing in polynomial time, right? So every L prime in pH reduces to L in polytime. But what does that mean? That means that you can solve any problem in pH in sigma j to the p time because you can just transform it over to this complete problem. But this means that pH is a subset of the jth layer because we can just transform it over to this language L because we know it's a complete language, a pH complete language, and then we can just solve it using only sigma j to the p resources. So that means any problem in pH at all can be reduced to this problem. So that means that pH is a subset of this thing, of this particular layer. So that means if I look at, for example, the j plus 1th layer, that means that it's equal to sigma to the j, meaning there's only a finite number of levels. Okay, so so things like that about being able to try to separate NP and P space, or separate P and NP, or P space and X time. Looking at things like this and looking at a restriction of a complete problem for, in this case, P space, could you get something kind of a hierarchy in between? And so people have been trying to study the polynomial hierarchy. There are papers published every year about this problem is in this particular class, say the sigma j, third layer or second layer, something like that. Okay, am I boring you yet? Just a little bit. Okay, maybe one more thing, and then I'll tell you to go. So I'm looking at my notes here. So we're faced with NP complete problems all the time, or even P space complete problems, right? So think of the clique problem again, right? So you're given this M and K, it's not M. You're given the G and the K thing. You're given a graph in the integer K, and you want to know if there's a K clique or not, right? But it seems like most of the time, you're asking about whether there's a triangle, a 3 clique, or if there's a 4 clique, or a 5 clique, right? But of course, if I fix K to be 5, then can you do this, solve this problem in polynomial time if I fix k to a value? Yeah, we've argued how to do that, right? You just look over all such subsets, there are only polynomially many of them, and then just check for each of them. But we still want to have k be part of the input, but it seems like most of the time, if we really want to solve this on a real computer, then k is very often a small number, right? But we can't say, well, it always runs in polynomial time because k is part of the input still. So k could still be larger, but still not a fixed number. So we need to, so what people have been doing really recently is looking at something called parameterized complexity. So what this is trying to say, well, we have these NP-complete problems, but most of the time, we're looking at small instances of this thing called the parameter. So k here is the parameter. So most of the time, k is small. And then maybe we can say, well, if k is small, then do I have a polynomial type algorithm, or does it still run for a long time? So what people usually look at is a class called FPT. So what this stands for is fixed parameter tractable. And some people have proved that certain versions of games and graph problems and network problems belong to FPT. So what the name kind of indicates to you is, if I fix a parameter to a particular value, then this problem is tractable. So tractable means polynomial time in this sense. But then, of course, you can define, well, maybe not all polynomials, maybe like n log n or something. So then you could define it there, but it's easier to just look at polynomials here. So here, what we're going to be given, so this, of course, is a set. So you're going to be given a tuple. So you're going to be given a language L and the parameter k. So if we wanted to do the same thing for clique, it would be clique comma k. So it's the language with k. So here, for a given W in L, solvable in the size of the input to the power f of k time. Oh no, sorry. I'm looking at a different one. It should be this. Solvable in the size of the input to a fixed constant. So I'm not restricting you to like squared or cubed or whatever, but I'm going to multiply it by f of k, where the f function is arbitrary. Okay, so if we have an algorithm that runs in polynomial time, ignoring the parameter, then we say that's fixed parameter tractable, because if I fix the parameter, the rest of the algorithm is tractable. Okay, do I have enough time for that? And then another one that people talk about is called XP. It's the same thing. It's solvable in where we say the input to the power f of k time. Oh, this should be time too. So here, this could be not necessarily a polynomial in the size of the input. So it seems pretty clear that XP contains FPT, because FPT insists that you have a polynomial runtime in the size of the input, whereas XP can be arbitrarily slow. It can be any arbitrary function in the exponent there. I actually don't. I do know why it's called XP, experience points or something, but it's actually called slice-wise polynomial. But you don't need to know that. But here we can actually say that P is a subset of FPT, which is a subset of XP. And the essential reason why that is for P, if you just ignore the parameter altogether and just run the algorithm itself, just ignore the parameter, well, the algorithm runs in polynomial time anyway. So therefore, it's in FPT. The f of k doesn't actually matter here. And I've already argued why FPT is a subset of XP, because XP can have an arbitrary function upstairs, whereas FPT must be a fixed constant there. Okay, and there's a whole lot more you can do here. You can talk about what are called hierarchies between FPT and XP, which people try to do to separate FPT and XP, but no one knows, again, whether or not they're different. So it's kind of like an analog of P and NP in some sense here. Any other questions before I let you go? So hopefully this will get you to think, well, some people are trying to solve problems that are real-world problems using theoretical concepts. I hope the class was interesting. I'll see you on Monday.